Okay, let's go into our studio. I'm going to go into the server version. Today what I want to cover is to go to chapter 8. As I mentioned, what I was covering in the early chapters was basically a review. And technically chapter 8 is a review too. It's very unlikely that you've seen this, using R code, even if you've done the relatively simple things we'll be doing in this chapter. You probably have not done them using R code. So I'm going to bring up the chapter 8 notes, and this is in Markdown. And I should mention that I also have these notes as sort of an official slideshow. I don't know that I gave you this. This is actually the same thing using LaTeX and R. But I'll show you what the output. I'll show you what the output looks. Actually, maybe I'll execute it just to show you how that works. You notice this file where my cursor is. It's chapter8.rnw, and the NW is a term that comes from Donald Knuth, who developed the TeX processing language for doing mathematical typesetting, and it's actually used widely in many fields. And LaTeX is built upon the TeX typesetting system. It's actually an extensive set of macros. And the NW means no web. Basically, it was what he developed to do literate programming. And the idea was to have the code self-documenting. So you included the documentation for the code along with the code so that someone else could take the code and understand what you did. And RNW is R's version of literate programming. Now, since then, of course, as I mentioned, I think I mentioned it was John Gruber, who was a blogger, who developed Markdown several years back. And it's a very simple version. It's not LaTeX, but it sort of has the same purposes in that it's a markup language, much like LaTeX and much like HTML for the web. But it's much simpler than either HTML and certainly simpler than LaTeX. And RMD effectively takes the Markdown language and it gives you the ability to add R code to the markup language, and it's very simple to learn. If you look at the code for LaTeX, it's actually much more difficult. And I was looking for something that students could easily learn, and I felt this wasn't it. In order to execute this, again, there's R code embedded in it, and I can show you some places that it is embedded. For example, right here, that's actually R code. And you notice the less than, greater than, equal says I'm going to begin a chunk of R code, and the @ sign at the bottom says that's the end of that chunk. And so it divides everything into chunks. And so if I want to execute the whole file, of course I could do it line by line, at least the R code in it. I can simply say compile PDF. And what this does is something similar to what you were doing before. And it actually created a PDF file. So if I go down and look at chapter 8 PDF, now again, since this is the web, I kind of have to do this twice. It says try again, and when I try again, it actually in this case creates a slideshow. This is a PDF slideshow that you can use with a clicker and so forth. Now there are ways So this is what it looks like in LaTeX. Notice that you have the R code in the output, for example, here. So I didn't want to require that. It's something some of you may want to learn, simply because it's a very powerful tool to learn. And if you're going to do a book, this will be the way you do it. So if you look at the book I'm developing, I am using a system called SWeave, which is in fact what generates all this. And SWeave is part of R. So that is the .rnw files. But what we're going to do instead, and let me set the working directory. So if I set the working directory, I'm going to knit it, and in Markdown it will create this type of document, which is the visualization of an HTML document. It actually creates HTML, and then this is the result. As I mentioned, you're going from this, and you can look at how I did it, and then compare it to the output, which is here. So for example, if you look at this first sentence, a central problem in statistics is making an inference about a population mean mu. And for example, you want to test the hypothesis that mu equals mu naught, where mu naught is some specified value. And then you have some alternative hypothesis that it's not equal to mu naught, or it's less than mu naught, it's greater than mu naught. We can do that with the t-test. Now, most of you have, or should have had, the t-tests. If you have not, or if you are rusty, you might want to go back and read Chapter 8 very carefully. The t-test simply takes the mean of the data, x bar, minus mu. And in this case, under the null hypothesis, you would put mu naught in there, divided by the standard error of y bar, which is s, the standard deviation over the square root of n. So the t-test is very simple to compute. But one of the things people forget about it is that there are certain assumptions that are associated with this t-test. The t-test is often used for small sample sizes because if n, the sample size, is quite large, the t-distribution is approximately the same as a normal distribution or a z-distribution. Now the t-distribution, like the normal distribution, is it's symmetric and has a mean of 0, but it has a greater variance. So if I go in and look at the text, and again, you should assume that the notes I have should be supplemented by reading the text. Oh, I went this. So here's what I've been working on. I'm going to do it as a single. So if we go down to Chapter 8, the student's T, there are the formulas. Now, correspondingly, the Z is defined as the same thing, except you either assume you know the standard deviation, so the population standard deviation is sigma, or you assume that n is so large that S, which is the sample standard deviation, is very close to sigma. But at any rate, you can see that the distribution should be about the same, but notice the t has two random variables. The t has y bar, which is random. If you get a sample and you compute y bar and you compute s, and then you get another sample from the same population and compute y bar and s, they're not going to be the same. What we're saying is they're random variables. But if either you know sigma, which is not really likely, or if in fact n is quite large, then S is going to be very close to sigma. then we could use a z-test instead of a t-test. So I don't know if you can see that, but the t-distribution is the one that has fatter tails. It's spread out more. The normal distribution is the one that, they're both sort of bell-shaped, but the t is more spread out. Why is it more spread out? It's more spread out because there are two random variables in its definition, so it's more variable, whereas the z only has one random variable, a y bar. So if you look at that, you'll see it's more spread out. I don't know if I have any. The book talks about certain properties. It's unimodal, it's symmetrical, and it's symmetric about 0 in particular. But it depends on the degrees of freedom, which we'll call nu, which is n minus 1. And the variance of the standard normal, z, is what? It's 1. Yeah, so the standard normal has a mean of 0 and a standard deviation of 1, whereas the variance of the t-distribution is the degrees of freedom over degrees of freedom minus 2, so it's nu over nu minus 2. But what happens is nu gets big. That approaches 1. So in other words, the t looks more and more, the spread becomes less and less, and it becomes more like the spread of a normal distribution. So it's approximately standard normal if v is large. And you can, in a mathematical statistics course, you can prove that to be true. Now, if you want the quantiles of the t, in other words, if I want the 95th percentile or the because it's symmetric, the 95th percentile is equal to minus the 5th percentile. So if you look at the distribution, if I look at the t, if I look at the area on the right side, and if there's 5% of the area beyond this quantile, then the corresponding value on the left, where I have 5% less than that quantile, will be minus t. So it's symmetric, so it's easy to find the upper and lower quantiles, which you need to do when you're testing hypotheses. And we'll show how to do this in R. By the way, this shows you what happens as you change the degrees of freedom. So if you look at the most spread out curve is when the degrees of freedom is 6, and when you increase degrees of freedom to 12, it's getting more like a normal, and as you keep increasing it over, as n gets larger and larger, it will converge towards the standard normal distribution. And usually by the time you hit about n equals 30 or close to that, then you're pretty close. So if you look at elementary stat tests, they often say, well, if n is greater than 30, go ahead and use a z, because we all know what the quantiles are for the t. Maybe you don't. They're about plus and minus 2 for the 2.5% on each tail, which gives you a 5% test, the significance level. In fact, they're really 1.96 and minus 1.96. So we often compute the z, and if we're going to do a test hypothesis, suppose you're testing that the hypothesis is 10, and say you take y bar minus 10 over the standard error of y bar, and if that's greater than 2 or less than minus 2, we reject at the approximate 5% level. So again, you should go back and sort of review that. Let's take a look at how we do the t-test, though. But one of the things I want you to realize is a lot of people blindly compute t-tests, and they say, and the question is, well, what are the assumptions of this t-test? Well, we have assumptions, normality being the key one. We're assuming that we don't know sigma squared, but sigma squared, which is the variance, is unknown. And that's almost always the case. You almost never know the variance. In fact, you don't know the mean either. That's why you get a sample. You compute the sample mean, the sample variance. But as I said, if n is quite large, then you can approximately say you can approximately say that we can used a z-test instead of a t-test. Now let me ask you this question. Does anyone know what the central limit theorem is?
When n gets large, the mean is equal to the sum. The variance equals to the variance of sum divided by square root of n.
Well, but what is the distribution? In other words, suppose you're saying, I don't know whether y bar is normal or not, and maybe it's very skewed. Maybe it's uniform. Maybe it's some distribution that's very, very different from the normal. So if you look, if you go in and, for example, if you go in and look at probability distributions, and if you look at some of these distributions, let's see, this is actually what's called a geometric distribution. Suppose I say, well, how many times do I have to flip a coin before I get a head? Well, it can happen on the first toss, right? So it could happen, and what's the probability it happens? It's a half, right? Yeah. So what's the probability it happens on the second toss? Well, you have to get a tail and then a head. They're independent. Let's assume they're independent. So then it's a half times a half or a fourth using the multiplication rule. So the probability y equals 2. If y equals 1 is a half, y equals 2, the probability, is a fourth. So what's the probability that you get it on the third toss? In other words, a tail, and then a head. Well, it's a half times a half times a half, right? Because the probability head and tail are going to both be a half, so it's going to be an eighth, and so forth. So that doesn't look very normal, but yet if you sample from this distribution, and n is large enough and you compute y bar, it's approximately normal, even though it's a discrete distribution. Now if we look at a continuous distribution, these are examples of what are called exponential distributions. They decay exponentially in time. And these are exponential distributions with different rates of decay. Now let's suppose you're sampling for an exponential distribution of a rate of decay of 1.5, which I think is this middle one. Even if you sample from that and you compute y bar, as n gets bigger and bigger, y bar becomes more and more normal, the distribution of y bar. Y bar has a distribution too. It's a random variable, so it has a distribution. But the distribution y bar will be approximately normal, even if that's your parent distribution. So even if you have a highly skewed distribution like this, if you compute y bar and n is big enough, you arguably can use a t-test. Because if n is big enough, then you're probably going to do a z-test. But at any rate, or at least it doesn't matter. Software doesn't do z-tests, it does t-tests. It's just that they're essentially the same once n gets big. So your software is not going to do a z-test, it'll do a z-test. So again, what I'm urging you to do is to go back and sort of review. This is a good chance for you to do it. You got Monday off. You got a number of days here before we meet again next Wednesday. So if you feel you need to be reviewing, then review the early chapters of the book. Okay. So what I want to talk about is inferences about a single mean. So we're gonna talk about a distribution where we have a sample. So let me go back to the code and let's take a look at an example. I want you to realize, though, that we have assumptions and you should check the assumptions. The key assumption here is normality. And that's particularly important if n is small. If you have a small experiment like 10 or 15 or 20, and that may happen for various reasons, it may be very expensive to get your data, so you can't get a lot. Or maybe it's just hard to get. Maybe it's not expensive, but hard to get. And if that's the case, n may be small. And if n is small, then the normality assumption becomes quite important. So the key thing I'm trying to say here is that you should check the assumptions. And if you have doubts about the assumption, this t-test is not valid if n is small and you violate the assumption of normality. So I'd like to take a look at an example Um, see, um, people hypothesize, if you have marathon runners, that at about 17 miles, there's a phenomenon called hitting the wall. That's where you sort of surpass, even if you train to run, unless you're extremely well trained. When you may do fine until you hit 17 miles, but somewhere in that area, suddenly it becomes extremely hard. So someone wanted to test this. Is 17, that's sort of the folklore that you hit the wall at about 17, but had anyone collected data and really said, is this true? So suppose you have an experiment that collects some data from runners, and you get them to report roughly where they were when they hit the wall. Apparently, it's a fairly dramatic change from one state to another, that you can tell. Any of you run marathons? So you can't verify this. At any rate, so here's the data. There are 12 runners that were measured, and there are the values, 15.8, 16.5, and so forth. So I'm actually saying miles gets. I could say equals. We could use equals instead of gets. Gets is a less than and a hyphen. And C is the concatenate function. It means concatenate the data together into a vector. In this case, it's a numeric vector. And the next thing I'm going to do is compute the length of miles, which is 12. Now, if I would have said n gets length of n, what would have happened without the parentheses around it? Why not?
It's 12.
It would assign 12 to n, but it would not have printed it. In other words, what we're doing is we're binding we create a symbol called n, and we're binding the value of 12 to it. And that 12 is computed by a function called length. So we bound the length of miles, which is a vector, the length of the vector, to the symbol, or in this case, we'll call it a variable n. And the parentheses around it, if you try it, without that, it will not print. So if, for example, I simply execute this, and then let's suppose I just say, well, if I say length of n, it will print, but it won't save it. So if I say length of n, whoops, did I misspell it? Oh, length of miles, sorry. If I say the length of miles, if I could spell this, GTH. And now what am I doing? Oh, I brought back the wrong one. This is not a good start. This is why I shouldn't record the lectures. So, at any rate, it's 12. Now, if I bring this back, and if I do, by the way, if I do a Control A, hold down the Control key and hit A, it jumps to the front. If I do Control E, it jumps to the end. So that saves some time. So if I say n gets this, it assigns the length of miles to n, but it doesn't save it. I mean, it doesn't print it. If you actually now, if I would now say n, it would say 12. But now suppose I put a parenthesis here, and I put a parenthesis here at the front and back, that saves it and prints it. So in other words, it saves a step. If you know you want to print it, you can put parentheses around it and it will print. Essentially, every expression in R has a default print. It may or may not be the default what you want, and you may have to do a more sophisticated type of print, but there is a default print for essentially every R object. Okay? So if I just say the length of miles, it computes it and gives you 2, but it's gone. Doesn't save it. If I save it to n, in this case, then n is bound with the value 12 in this case. And n is saved, but it is not printed. If I put parentheses around it, I save it and print it. Is that clear? So in terms of some of the notation I do, you should, these are just a few things. Now the next thing I'm going to do is I'm going to compute the mean of miles, and I'm going to save it in m, the variable m, or the symbol m, and I parentheses so it's going to print it. So the mean is about 16.69. It doesn't seem too far from 17, right? But is it significantly, in other words, is that far enough from 17 that I would reject the null hypothesis that mu equals 17? So if my null hypothesis is mu equals 17, would I reject it based upon a sample mean of 16.69? Does that make sense to you? So in order to do this, we need the standard error. So let's first of all, we can compute the standard deviation. Now, one of the things I want to you to notice about this, I keep doing that, and I mean to do this. Here, by the way, to do line by line, I click on Run, and that will do it line by line, and it moves the cursor down to the next one. I want you to look, the first function is mean. It simply computes the mean of miles and saves it to m. And because it's parenthesized, it prints it. In the next one, I have the variance of miles. VAR is the variance of miles. But if I take the square root of the variance, I get what? Standard deviation. Now, there's something very important in that last expression. The square root of the variance of miles. And what is it? Can anyone tell? I have a function embedded as an argument of another function. I have a function within a function. In other words, the function variance is an argument to the function square root. So R is a functional style of programming. So this saves time. I don't have to say the variance of miles and save it, and then say the square root of what I saved. I can do it in one step. So your programming can become very concise. So if you're programming in a language like C or Java, you may take this much code. For those at home, it's about 2 feet of code. And if you do it in R, it might be 6 inches of code. And that's because R has very high-level operators, plus it supports a functional style of programming. So when you're programming in R, you can often write or do a lot with a very small amount of code. Now, I don't know if I mentioned this to you. I think I may have, but I'll emphasize it again. Isn't it a lot easier just to use SPSS or jump and point and click? So why not just do that? Yeah, there are a lot of reasons why. Let's suppose there's something for jump and SPSS. Now SAS really you have to program too for the most part. They do have some graphical stuff, but for the most part in SAS you're also programming. But you're not programming in the same sense you as are. You're mainly doing data structure programming. You're programming the data stuff. It's not a full programming language. But it's fairly powerful for doing data management. In fact, the reason that SAS probably crushed SPSS, and they were both developed SAS was developed in the late 60s and early 70s, but it was really in the late 60s where the philosophy of SAS was developed and laid out. And SPSS may have been a little bit later, but again, it's been around a long time. But SAS is huge, and SPSS has been bought by IBM. But SPSS is not nearly as big as SAS. If you go to the SAS campus down in Cary, North Carolina, it's maybe 5,000 or 6,000 acres with a huge number of buildings. It's one of the largest private corporations. Why was it successful? It was primarily because it was very, very good at data management. It was also, from the very beginning, because mainframes, even back then, did not have a huge amount of memory. So they designed SAS from the very beginning so that memory was not a constraint. In other words, it could do processing very efficiently using the memory resources, what might be called out-of-memory processing and so forth. But R has essentially no bounds. Obviously, if you're going to do a t-test, it doesn't kind of matter where you do it. But increasingly, no matter what your field is, if it's in ecology, increasingly ecologists using R, and increasingly I see books in ecology, statistical ecology using R and so forth like that. There's an increasing, and if you look at almost any field, if you look at Springer-Verlag and if you look at CRC, each of them has a huge series in R. There are literally hundreds of books now in almost every field that uses R. And it's because there are really no limitations on what you can do. And I mean, I wouldn't say no limitations, but it's amazing how far the bounds have been stretched in what you can do. So there are several reasons. I hear various people saying, well, why don't you use MATLAB? Or why hasn't it become popular among statisticians? Why hasn't Mathematica become popular among statisticians? Well, there's a reason. And that is that R was designed from the ground up to do statistics. And it works the way, not only the way we think, but it has very powerful data structures, and it has very powerful functions, plus it has this functional style programming. Okay, back to this. So now we can simply say I want the hist of miles, and so this creates a histogram. And if you actually look at the function, I can control that histogram. That's the default histogram, and I'm not doing anything. I just say hist of miles. And by default, it puts miles down here, and it does a frequency. But suppose you want a probability plot instead of a frequency, or suppose you want to change the groupings such that they're different than that, and so forth. You can do this in a very sophisticated ways. I could embed mathematics. I can embed mathematical expressions typeset here and here on the graph. In other words, I'm not limited. So if you actually go here and let's look at help for a minute. One of the things you should get accustomed to doing is type in help commands just to see what the options are. And it's very nice because if you're programming it on the left, you can bring up the help on the right to help you you're not going to memorize all the arguments to hist. And so as you're programming and you say, well, I'd like to create a really nice graph, and so I want lots of options. Well, then what you probably want to do is bring up the help for histogram on the right so that you can determine, well, what options do I want? Do I want to specify the x limits, the y limits, etc.? And do I want a probability scale, frequency scale, and so forth? So this describes how you plot. You can plot line charts. There's all kinds of options that you have that you can do with histograms. So, and this explains what they are, and then gives some examples. And they always give, and then the output values, and then they always give examples at the end, and you can actually execute these examples if you sort of want to see what happens. So you should get accustomed to looking at the help files. Now let's go back. So there's a histogram. Now we had an assumption of normality. So how are we going to check that assumption? Now there are formal tests of normality. In other words, if you look at the literature, you can formally test whether or not the data follows a normal distribution. The problem is that these tests are not very powerful. Now, what do I mean by not very powerful? you're going to test a hypothesis. If you do a formal test for normality, you're going to have a null hypothesis. The null hypothesis says, my data is normally distributed. What do you think the alternative hypothesis is? It's not normally distributed. Now, can anyone tell me what the power of a test is? In simple words. It's the probability you reject when you should reject. In other words, it would be the probability of saying it's not normal when in fact it's not normal. So, if you don't have power, that means even if it's not normal, you tend to say it's normal. You fail to reject. So if you have low power, you tend to say it's normal, even if it's not, if you have low power. So you feel good because you tested it and you failed to reject and you said, oh great, I have a normal distribution. But maybe you don't. This graphical representation, there's one thing we're fairly good at, and that is we can tell whether something falls along a straight line. And this is a normal probability plot. A normal probability plot is going to plot the sample quantiles against the theoretical quantiles of a normal distribution. Now, I'm not going to go into this in a huge amount of detail about exactly how these theoretical quantiles are computed. But just think of it this way. If I think about the lower quartile, which is the 25th percentile of a normal distribution, and you get a sample, and if you get a sample, you can compute the sample quartile. It's about, if you rank the data from smallest to largest, it's about a fourth of the way through, right? I'm being, not quite so accurate when I say that because there's a technical definition of what the sample quartile is. But you've got a sample quartile, and you've got the quartile from a theoretical normal distribution. Are they the same? Now, we do this, in fact, for every data point, we can compute the theoretical quantile for a standard normal distribution, for a standard normal. And then we can compute the actual data against those theoretical quartiles. And if, in fact, you're sampling from a normal distribution, we should approximately have a straight line. Now, having said that, the slope, you might say, well, does it have a slope of 1? Well, if you plot it against the actual normal distribution instead of the sample distribution, the theoretical distribution of a standard normal, it is true that the slope would be 1. But we don't know what what we're just saying is, I just want to know if it's normal. And if I plot it against a standard normal distribution, I'll still get a straight line if it's normal, but the slope won't be 1. But that doesn't matter. I don't care what the intercept and slope are, quite frankly. I just care, is it a straight line? So if I look at that, there's a little bit of curve. It's not too bad, is it? There's a little bit of curvature. And that actually means if, in fact, the curvature went more in the direction of convexity, where it's sort of sloping up, that would imply that I have a right positively skewed distribution. This might imply that it's skewed a little bit the other way. And I don't know. You see, I don't know if we can really tell from this data. It seems like this says that maybe it's skewed a little bit to the left. But again, we're not very far off. In other words, this is sort of concave downwards. It's sort of saying that we have perhaps a little bit of skewness, but in this case, if anything, it's skewed to the left, not to the right. Now, most data, if it's skewed, tends to be skewed to the right. You get long-tail distributions to the right. That's very common. If you look at the wealth, if you look at the income of Americans, it's skewed to the right. Well, there are actually theoretical distributions we could try to fit to those incomes. There was a nice graph I saw. I can't remember it, where you could animate it. and it fit the income distribution over time. And the idea is to see, is the disparity between rich and poor getting greater? What do you think the result is? Yes. It's a nice little animation. You can animate the distribution by year and watch how the distribution changes over time. Okay, now, if we are going to test a hypothesis in our example, if we were going to test a hypothesis that mu equals 17, we've computed the sample mean, we've computed S. S is the square root of the variance of miles, right? We computed both of those. We computed X, we computed Y bar, we computed S. And so if we wanted to compute, a t-test or a set of confidence interval, we can easily do that now. So does anyone know how you do a confidence interval for mu? Yeah, we're going to take y bar plus or minus the t quantile times s over the square root of n, which is the standard error. So again, if I look in the book, there should be by the way, that's that same plot with a sort of non-parametric fit. And you can see the skewness of the distribution. This is the cumulative distribution function on the right upper. So if I want, and that's an approximate fit to the little dashed line is approximate fit to the cumulative distribution function. If I wanted to find the 60th percentile, how would I do it? On the y-axis, I would go to 0.6. I would go over till I hit a vertical line, or you could hit a smooth line. Let me comment on that a minute. So at 0.6, I go over till I hit typically a vertical line, and then I go down, and that's the quantile. That's how you can compute a quantile from the real data. What happens if I go over and I hit a horizontal line? There's no unique quantile. You could pick any number from the start of the horizontal line to the end of the horizontal line. Typically, you may use the number in the middle. But if I hit a horizontal line, if I exactly hit it, there's not a unique quantile. So if I have 5 numbers, how do you compute the median? The median is the 0.5 quantile or the 50th percentile, however you want to say it. The median is a quantile. It's the 50th percentile or the 0.5 quantile. How would you do it? What you would do is you would rank them from smallest to largest, and you would pick which one? The third, and it's unique, right? Suppose I have 6 numbers. You rank them. What's the middle one? What's the middle one?
Take the average.
You average between the third and the fourth. Well, that's exactly, that's what's happening. You're hitting a horizontal line. So typically we average the low and the high within that horizontal line to use that as a quantile. You wouldn't have to. You could use the minimum if you wanted to. You could. But typically, by convention, we average to get the median. By the way, let's see. This plot is actually the same plot, except for the fact that the axes are flipped. The normal quantiles are on the y-axis and the miles run on the x-axis. And therefore, it appears to be, it's curved up instead of curved down, right? There's a straight line that's actually fit to that. If your data is highly skewed, how do you think how do you think that straight line is fit? Actually, there are various ways of doing it. I used a function called QQLine. I think what that does is it fits a straight line through the quartiles. The problem is, if you've got an outlier, or you've got a highly skewed distribution, you might say, well, if you know linear regression, you might say, well, I'm going to fit in a linear regression. And we'll do that in chapter 9. So if you don't know linear regression, we'll get to it next chapter. But you would say, okay, I want to fit a line. I'll just fit a linear regression. That's actually not a good idea. Because if you've got an outlier of skewed data, it greatly affects the slope of that regression line. And I'm trying to have a robust line which is not influenced by skewness and outliers. So instead of fitting the line using linear regression, it's better to fit the line through the two quartiles because the two quartiles are far enough in the data that they're not so much affected by long tails, skewness, or outliers. So it's better to actually, 2 points determine a line, right? So I could simply fit the data for the theoretical quartiles to the sample quartiles and fit a line. So I could take the 2 points and fit a straight line. Sample quartiles map to the theoretical quartiles and fit through those 2 lines. I believe that's what was done. At any rate, I don't know, does the book, I'm not sure this is in the book. Let me see if I can bring up that program, Reflector. Let me see if yeah, play ports unavailable. That's not good. I don't know why. Maybe this has to be on. Well, let me just talk about it. Has everyone in a previous course done confidence intervals? So, if you've had any course at all, you should have done confidence intervals on mu. If not, you need to review this. But if I want a confidence interval on mu, and I've got y bar and I have s, then what's the confidence interval? I need a lower limit and I need an upper limit, and I need to pick it so that I have some probability of coverage. Typically, we might do 95% coverage. So we want to say, I'm 95% confident that mu is between this lower limit and this upper limit. I don't know mu, but I want to be able to say I'm 95% confidence between these 2 limits. So how do I compute the limit? Well, the lower limit is simply the mean minus this 0.025 quantile times s over the square root of n, which is the standard error of y bar. And the upper is y bar plus that 0.975. And the reason it's 0.975 instead of 0.95 is I want 2.5% on each end to get a 95%. Times s over the square root of n. So I want you to look at r, because this is exactly the way it's computed. If you look at L gets m, which is the mean, minus the t quantile. Now, I had computed the t quantile here as qt as 0.975 with n minus 1 degrees of freedom. And that t quantile is 2.201. Now, if n would have been large, what would that number have been? Yeah, 1.96. It would have been 1.96. It would have been the upper quantile 0.975 of z distribution, which is 1.96. Now, often we say the confidence interval is simply y bar plus or minus 2, times the square root of n, because 2 is close to 1.96, and it's simple to remember. We want a confidence interval, y bar plus or minus 2 times the standard error, which is s over the square root of n. What do I mean by the standard error?
Standard division over the sample size.
Yeah, well, but I mean, y bar has a distribution. By the central limit theorem, it will tend to be normal, even if the underlying distribution is not. Since it's a distribution, it has a mean and a variance. The mean is the same as the parent distribution. The parent distribution has a variance of sigma squared. So if the parent distribution has a mean of mu and a variance of let's say a standard deviation of sigma, then what is the mean and the variance of y bar? Okay, y has a mean of mu and a standard deviation of sigma. What is the mean and standard deviation of y bar? The mean will be mu, and the standard deviation will be sigma over the square root of n. In other words, the variance is less. I have more precise information about the standard deviation. So, in that case, I have more information if I know, if I have a larger sample size. And the bigger it gets, the variance gets smaller and smaller and smaller. So I have a more precise estimate. In other words, I can be more and more sure that y bar is close to mu. But is it close for n equals 12? Well, maybe not so close for n equals 12, but let's take a look at it. So I compute the quantile, it's 2.201, and then I take L is the mean, m, minus that quantile, which is negative now. It's a minus t. Now remember, the t distribution is symmetric. So if I want the 0.025 quantile on the lower end, I can get it simply as minus the 0.975 quantile on the upper end. So I have minus t quantile times s over the square root of n. You see how that's done in R? I mean, you can read it. And then u is m plus the quantile times s over the square root of n. And so if I compute it, it's 16.24 and 17.14. And so what we can say is we're 95% confident that mu is between 16.24 and 17.14. So, just from that, can you tell whether or not we reject or accept the hypothesis that mu equals 17? Yeah, we're going to at least fail to reject because 17 is in that interval. Since 17 is in an interval, we can say we fail to reject. Now, I tend to say fail to reject instead of accept, because accept is a fairly strong word. If I say fail to reject, it basically means accept with some reservations. In other words, why do I say that? It's because you don't know the power. You don't know the power. So we're not going to go way out on a limb and say, yeah, it's 17. We don't know what the power is. Now, you could compute the power for this simple example. Okay. Well, let's go ahead and let's actually look at it as a hypothesis test now. Now, if I'm doing it, the t-test was what? It was y bar minus mu, and in this case, we're going to replace mu by the hypothesized value. We're going to ask how far is y bar, which is 16.1? Yeah, 16.24. We're going to compute, is that the mean? It's up here, 6.69. We're going to ask how far 16.69 is from the hypothesized value of 17. So we're going to take y bar minus the hypothesized value and divide by the standard error. So, that if we want to really compute a t-test, that's what I did right where the cursor is. T gets y bar, which I define as m, minus 17 over s over the square root of n. It's a minus 1.518. Now, if I were doing a formal test, I would say, does that fall in the critical region? And the critical region is determined by that quantile. And I can reject because it's too high or too low. I can reject because it's greater than 17, or I can reject because it's really less than 17. So since it's a two-sided test, I'm going to take the absolute value of t, and I'm going to say, is it greater than the upper quantile? And notice I'm saying greater than, and the answer is false. It's not, which means we fail to reject. Now, do you know the concept of a p-value?
Small level we can reject.
Yeah, it's sort of the probability that you get something as extreme or more extreme than your actual test statistic. And if the p-value is less than the significance level, you would reject. So if the significance level is 0.05 and I compute the p-value and it's less than 0.05, I reject. Software doesn't do significance tests. It gives you a p-value. It lets you conclude. It will give you a p-value. So you get a 0.03. You say, oh, that's less than 0.05, I reject. You get 0.07. Well, if you're testing at the 0.05 level, you wouldn't reject, right? But you would reject at the 0.1 level or the 10% level. So software is going to give you a p-value. So how do you compute the p-value here? And then I'm going to show you how the software actually does it. You don't have to do it by hand the way we're doing it. I'm simply stepping through it. So how do I get the p-value? Well, I'm going to take the absolute value of t, and I'm going to say, what's the probability I'm greater than that? So what does p of t? P of t is a function. It gives you the probability it's less than or equal to a value. P of t is a probability. It's like a cumulative distribution function. D of t gives you density. It's not a density. I'm getting the probability. It's like a cumulative distribution function. It's probability it's less than or equal to my t value. But I'm going to take the absolute value so that I'm in the upper tail. So I'm going to ask the probability I'm less than that. That's what I get first. And I subtract it from 1. What does that give you? The probability I'm greater than that. Now, since it's two-sided, I have to double it. Because I could have also gotten it by this extreme on the lower tail or the upper tail. So this is a very common thing, and I'll probably write a few on notes. I probably should actually draw a graph of this. But I'm taking in other words, I'm getting, here's my t, my computed t. And I do p of t of it. Okay? I get the absolute value, it makes it positive. Then I get p of t of it. And that gives me the probability I'm less than or equal to that upper value, the t, because I take the absolute value. And I subtract it from 1. That gives me the upper tail probability. Then I double it. And that's the p-value. And the p-value is, in fact, what? It's 0.1573. See, I would fail to reject at even the 10% significance level, right? If I rejected 0.05, I'd also reject at 0.1. In other words, I'm not that close. Now, that may bode well in terms of power, but again, we haven't computed the power here. So we fail to reject the null hypothesis at mu equals 17. Or we can compute it this way. There's a function in R called t-dot test, and you simply put miles, comma, mu equals 17, the null hypothesis. That's a little bit easier than what I just did, but I wanted you to see how we can use R as a calculator, right? Now, if you look at the result, if I just say t-dot test of miles with mu equals 17, it says, first of all, that the t-value is minus 1.518 with degrees of freedom 11, and the p-value is 0.1573. Those are all the numbers I have above, right? I didn't print out the degrees of freedom, but degrees of freedom is n minus 1, and n is 12. The alternative hypothesis, it is not equal to 17. Now, you can do a one-sided test here. In other words, if you look at the t-dot test function in the help, you can do one-sided test. And I think we'll illustrate that a bit later in this chapter. Then it says the 95% confidence region is 16.24 and 17. That's what I computed above, right? And then it gives the sample mean. By default, it's not giving the sample standard error or standard deviation, but it is giving the sample mean. So that's a built-in function. to do the t-test. So that's quite simple. So let me just start talking about, you should finish reading chapter 8 for next time. And you should practice and understand what we did in terms of the R code. So I'm just going to briefly introduce this, and then I'll probably go back and review it a little bit. We have a paired t-test. Now, one of the things we're going to be talking about in this course is how do you control variation. Now, if you wanted to compare two calculators, I could do that in one of two ways. I could get one sample of people that would use calculator A, and another group of people would use calculator B. If I do that, I may have a lot of subject-to-subject variability. Perhaps it would be better if I had each person use A and B. And perhaps I should randomize the order in which they do them. In other words, if everyone does A first, you may be practicing and therefore it can do B faster. So you should randomize the order in which you do them. Some people will have A first and others will have B first. So you can try to control, you try, in that case, you're trying to control a source of bias. But we're also trying to control the variability by having the same person do A and B. If we have less variability, meaning sigma is smaller, we have less noise, and therefore we can detect differences with smaller sample sizes. That's an efficient design. So this paired t-test is a very simple test that begins the thought process of how we control the variation. And again, by randomize the order in which you do the calculators, you're also controlling bias. So there are simple things you can do as a researcher to control sources of variation and control bias. So suppose you go out and you get a number of students, and they do A and B, and they're doing a certain sequence of tasks, and you time how long it takes. The task for A and B would be the same, and the test, everyone, of course, would do the same test, and you would do the same task on A or B. So the question is which calculation is faster? So I have my data. I have a data called Calc 8.3, which means example 8.3 in the book. And that's a little text file, and I read it in with a function called read.table. And I also have headers. In other words, the headers give me, if you think about an Excel spreadsheet, for example, you may have a column, you may have a row of headers which tells you what's in each column. Well, we have actually three columns here. We have the student, we have A, and we have B. So the headers are student A and B. And so we read in the headers. That says header equals true. It means we do have a header line. And then we read in the data, and I then print it out. Now in this case, this is one of these little examples in the book where it says let's do it by hand, and therefore we only have 5 students. Obviously, if you did this in a more realistic setting, you would have more than 5 students do this, because you're going to have very little power with 5 students, right? So how could we do it? I claim that we could just say t-test of A minus B. What hypothesis are you testing here? You're testing that the difference has a mean of 0. So by default, if I don't specify the null hypothesis in that function, it assumes you're testing that the mean is 0. In this case, the mean is a difference. Because I'm really testing mu sub d. I'm testing that the difference is 0, meaning the two calculations, the mean, if I take mu of A and subtract mu of B, so mu of A would be the mean of the A calculator, mu of B would be the mean. We're testing that that difference is 0. So there's the test. And notice that the t-test is the t-value is 2.324. And why? There must be more data than that. Oh, I see. I'm only printing out. You see, I misread that. If you look at calc, look at that second line where it says calc C. Brackets 1:5 comma, and then there's nothing. square bracket is a subsetting operator. And since I have a data frame, I have a data frame which you can think of as a jump data set or a SAS data set or a jump data table. I have a data frame that looks sort of like a matrix. It has 3 columns. And in fact, there are 12 students here because the degrees of freedom is equal to 11. And the 1:5 expands out to what? Yeah, 1, 2, 3, 4, 5. And that says on the right-hand side of I'm on the left-hand side of the comma, I'm picking rows. On the right-hand side of the column, comma, I'm picking columns. So I've got 1:5. It says print out the first 5 rows. And I have nothing on the right side of the comma, which means print out all. If you don't put anything, it prints all the columns. So this is going to print the first 5 rows and all the columns. Now I could have used a function called head. Head, H-E-A-D, is a function. So if I would have said head of calc, it would have printed, by default, it would have just printed the first 6. There's also something called tail. It prints the last 6. So if you want to do something quick, you could say head of calc. It would print the first 6. Now sometimes you have a lot of columns, and you only want to print out some of them. So this would let you pick and choose what you print out. At any rate, the t-value is 2.424, degrees of freedom is 11, and the p-value is 0.04. And that would mean what? That would mean we reject. There appears to be a difference. And notice that, well, notice that the confidence interval does not include 0. And, well, we'll start there next time. Is this? Yeah. So we'll come back to this. I'd like you to start working through the R code here. In a not too distant future, you'll get your first assignment. If I post the assignment this weekend, I'll probably email you sometime this weekend with updates, including the possibility of having an assignment. The assignments, the intent that I have is to give you a template for the assignment in our markdown, and then you sort of fill in. So I'll probably try to do this weekend so that you can sort of get accustomed to how we're going to give assignments. But I'm going to give you a template, and you can fill in the R code, and perhaps an explanation of what the results say. But generally speaking, you're just going to enter a little bit of R code, and you're going to have a little bit of text that may explain your answers. It's not going to be lots of mathematical typesetting and all that stuff. Okay, any questions? Okay. Have a good Labor Day weekend.